We often think of the world of imagination as something different from the world of reality, an escape into a purely mental realm of our own creation. But in fact, imagination can offer a wonderful route into reality, really understanding what's happening around us, rather than just watching it, often requires thought that extends beyond the real into contemplation of what could be, or ought to be, or even into what can't be. In this lecture, I'll use some famous thought experiments as illustrations for more general strategies of effective problem solving. What these strategies have in common is the attempt to solve real problems with something distinctly unreal, the imaginative world of thought experiments. In a previous lecture, I talked about visualization and gave you a proof of the Pythagorean theorem with no math at all. Later in this lecture, I'll outline an Einsteinian thought experiment that lies at the core of relativistic physics, again with no math. I'll start with an example that emphasizes an extension of the visualization strategy. It's the strategy of going to extremes. How do you solve a jigsaw puzzle? Most people start at the edges. They go to the extremes because they're easier. Once they know the layout there, all the rest becomes easier. So try going to extremes in this example. There are two flagpoles, each 100 feet high. Tied between the tops of those poles is a 180-foot rope, which dangles 10 feet off the ground at its lowest point. How far apart are the two flagpoles? If you draw a picture, it'll be a picture of two flagpoles with a curved rope between them. At the bottom of the curved rope, you'll mark the bottom is 10 feet off the ground. But how far apart are the two flagpoles? If you want to try the problem on your own, press pause and come back. Some people might try to solve that problem by getting out a textbook and looking up parabolas. But there's a much easier way. Consider the extremes. What's the maximum distance the two flagpoles could be apart? 180 feet, since there's a 180-foot rope between them. At that extreme, the rope would be stretched taut, 100 feet from the ground at every point. How about the other extreme, the minimum distance apart? Well, they could be right next to each other. The 180-foot rope would just dangle down 90 feet on each side and 10 feet off the ground. We found the answer by going to extremes. The two flagpoles have to be right next to each other. Here's another one. We have an eyewitness to shoplifting in a coin shop. The witness says that the suspect had 6 pockets and that he saw him steal precisely 20 silver dollars. The report, he left with exactly 20 silver dollars in his pockets, at least $1 in each, and a different number in each pocket. Should we trust that eyewitness? Press pause if you want to think about it. We can use the strategy of going to extremes to examine the credibility of our eyewitness. With a different number of dollars in each pocket, the least number of total dollars has to be 1 in pocket 1, 2 in pocket 2, 3 in pocket 3, 4 in pocket 4. The least number of silver dollars that can be divided between 6 pockets that way is therefore 1 plus 2 plus 3 plus 4 plus 5 plus 6. That totals to 21 silver dollars, not 20. The suspect couldn't have divided only $20 between 6 pockets in the way the witness said. He would have needed at least 21 silver dollars. We've just refuted a theory by going to extremes. The quickest way to refute a theory is often to find a counterexample, and the quickest way to find a counterexample is often to go to the extremes. What we want in our theories, in both science and in philosophy, are universal generalizations, natural laws that apply in all circumstances. You can see how powerful universal generalizations are if true. That's why we work so hard to try to get them. Their Achilles heel is that it takes only one counter case to refute them. If I say that something holds for all of a class, it'll take just one exception to prove me wrong. Galileo dropped a single cannonball and a musket ball from the top of the Leaning Tower of Pisa. The physics of the time was Aristotle's physics, and what Aristotle had said was that heavy objects will fall faster, a universal law. That theory fits most everyday experience. Drop an egg and an empty eggshell off the top of a building, and the egg will hit first. Even Galileo started out thinking Aristotle must be right. But when Galileo dropped a cannonball and a musket ball, they hit at the same time. All it took was a single experiment. One simple case, and Aristotle's physics was soundly refuted. Galileo's was a physical experiment. But Galileo also offered a pure thought experiment for the same conclusion without actually dropping cannonballs. It went like this. Aristotle says that heavier objects fall faster than lighter objects. So take an 8-pound cannonball. If you drop that, it'll be falling pretty fast. If you drop a 4-pound cannonball, Aristotle says it'll travel slower. Here's the thought experiment. What'll happen if you tie them together and drop both? Aristotle says that the 4-pounder will be traveling slower. So it seems it'll hold the 8-pound cannonball back, like a little kid holding back his big brother. On this reasoning, the two cannonballs tied together should move slower than the 8-pound cannonball alone. But wait a minute. Tied together, the two cannonballs make a 12-pound complex. So the two together should move faster than the 8-pound cannonball alone. Aristotle can't have it both ways. Without dropping anything, with just a thought experiment, Galileo put all of Aristotelian physics into doubt. Someone makes a sweeping and general claim. The strategy is to look for a simple counterexample that might put that claim in doubt. Here's a famous philosophical thought experiment regarding the claims of artificial intelligence. In the flush of early success in artificial intelligence, Roger Schenck at Stanford claimed that with the right program, a computer could understand English. By instantiating the right computer program, he claimed, a machine could do precisely what we do. It could understand a natural language, English or Chinese. The philosopher John Searle calls that claim strong AI, and he regards it as pure hype. His ammunition against it is a thought experiment. Searle builds a counterexample in which Schenck's program is running, in which any program you like is running, but no real understanding is going on. Schenck had said that running the right program would amount to understanding. But if the program can be running when no understanding is going on, running the program can't amount to understanding. That's the strategy. Here's the Chinese room. Searle imagines himself as a man in a room with a very large rule book. The book has a column of input symbols on one side of the page. They just look like squiggles to him, Searle says, with a set of output squiggles on the other. The book has rules for which output squiggles to use given certain input squiggles. The room has an in slot and an out slot. Pieces of paper with squiggles come in on one side. Searle consults the book, copies out another set of squiggles, and drops those through the out slot. Suppose, Searle says, that the rule book is Schenck's ideal program. Unbeknownst to the man in the room, the squiggles coming in the door are Chinese questions. The squiggles he puts out the door are Chinese answers. Given the right rule book, input and output would match inputs and outputs of any program that Schenck might want to invent. But wait a minute, Searle says. The rule book is just a rule book. It doesn't understand Chinese. The room is just a room. No understanding there. And the man is just following the rules. He doesn't understand Chinese. Schenck's program is running, but nothing in the Chinese room really understands Chinese. Searle points out that what a computer does isn't anything more than the guy with the rule book does. Nothing in the thought experiment case deserves to be called understanding, so nothing in the computer case does either. Searle's thought experiment took the debate into new and important channels, but it didn't end it. If following internal rules isn't enough to understand a language, exactly what is it that we do beyond that? Let me give you another philosophical thought experiment along the same lines, a single imaginative case intended to throw doubt on a grand general claim. This is Black and White Mary. It's a thought experiment from the Australian philosopher Frank Jackson. Jackson is out to show that there's something about consciousness that goes beyond the facts that science can give us. Mary is raised in a black and white world. Everything she sees is colored black, white, or some shade of gray, including her own image in a mirror. No color, just black and white. Despite that impoverished upbringing, Mary has become the world's leading expert on color vision. She knows all the scientific facts regarding color vision, derived, of course, from her extensive reading in black and white. One day, the black and white door is opened, and Mary walks out into the realm of color. Aha, she says, that's what red looks like. At that moment, Mary has learned something new. She now knows what red looks like. But she already knew all the scientific facts regarding color vision. The simple fact that red looks like that must therefore be something beyond scientific fact, something that science alone can't give us. Or so Jackson argues. Black and White Mary is famous for channeling discussion in certain directions, but Jackson's thought experiment can't be said to have settled the argument any more than Searle's did. Next to philosophers, those who love thought experiments most seem to be physicists. Maxwell's demon was a thought experiment that played a major role in the history of thermodynamics. Schrödinger's cat was a thought experiment central to debates regarding quantum mechanics. Here's a thought experiment crucial in the development of Einstein's theory of relativity. Just as he was a master of visualization, Einstein was a master of the thought experiment. Suppose a train car is moving along a track with Mike in the middle of the car. He passes Fred, who's standing on the platform. We assume that the speed of light is a constant. Bolts of lightning hit both ends of the train car. The light from the two bolts reaches Fred at the same time. He sees them hit simultaneously. What does Mike see in the middle of the car? Here it's crucial that the car is moving. The car is moving toward one lightning bolt, running up to and meeting the light coming from it. So Mike in the middle of the car will intersect light from that bolt first. The car is running away from the other bolt, adding distance for the light from it to travel. That light won't reach Mike until a little later. From Mike's perspective in the moving train, the bolt at the front of the train hit before the one at the back. It's called the theory of relativity, but it is in large part a series of deductions from the assumption that some things are not relative. What Einstein's thought experiment shows is that if the speed of light is not relative, observable simultaneity, whether two things are seen as happening at the same time, will be relative. Einstein also followed a firm methodological principle that theories must be written in terms of what is observable. When you rewrite this thought experiment purely in terms of what is observable, you can see how time and simultaneity will be relative to the comparative motion of two observers. That's the intuition at the core of Einstein's special relativity. Visualize. Go to extremes. If you're out to refute a theory, look for a counterexample. In all the examples I gave you, there's also something else at play. All of those involved using your imagination to simplify a problem. There are lots of ways to simplify. One is the strategy of analogy. If the problem you face seems resistant to your best attempts, think of a problem that's like it but simpler. Some problems are hard just because they have a lot of parts. For those, a strategy of divide and conquer can prove effective. Solve the parts independently, then put them back together. A complex solution for a complex problem, but made of simple solutions to simple ones. Both strategies can be illustrated with the classic Tower of Hanoi problem. This is a hard one. You have 3 posts in a row. The right and middle posts are empty. On the leftmost post are stacked a series of 6 disks, ordered from largest at the bottom to smallest at the top. Your task is to end up with all 6 disks in the same order as they are now, but on either of the other 2 poles. But there are restrictions. You can only move 1 disk at a time. You can only move a disk from one pole to another. You can't just put it to the side, for example. And you can never put a larger disk on top of a smaller one. So how would you proceed? How many moves do you think it would take you to get all 6 disks from one pole to another? Gosh, where should we start? Well, we can take the top disk and move it to pole number 2. Then the second disk has to go to pole number 3, because it can't go on top of a smaller disk. Now I guess that the one on number 2 has to go to 3. Oh, it's all so confusing, I'm lost. Cool it. Use a few conceptual strategies. First, visualize. You want to be able to see the problem. Maybe you were already visualizing the setup mentally as I described the problem. It's hard for me not to do that. Even better, draw a sketch of the 3 poles and the 6 disks. Then you can really see it, and not merely in your mind's eye. The best option of all is to get a 3-dimensional version. You can construct that yourself. All you need are 6 disks, each smaller than the one before it. You could see the problem in 3D even if your poles were just 3 spots on a table in front of you. Each step, from mind's eye to 2-dimensional drawing to the realm of 3-dimensional manipulation, is a giant step in visualization. We want to know how many moves are required to move 6 disks from one post to another inside the rules. 1 disk at a time from pole to pole, never a larger one on top of a smaller one. The first strategy, visualize. The second strategy, simplify. If a complex problem has you blocked, try an analogous problem at a simpler extreme. It may not be what you were asked to do, but it may give you a clue as to how to do what you were asked to do. So what if the problem wasn't about 6 disks, it was just about 2 disks? How many moves to transfer 2 disks from one post to another? That's easy. The top one goes to an empty pole. The bigger one goes to the other empty pole. The top one goes on top of it. That was 3 moves. But note that the top had to go somewhere that it didn't end up to allow the one underneath it to move. That's clearly going to be the case when we're dealing with more disks too. Smaller disks have to go someplace to wait until we move a larger disk underneath them. So the 2-disk problem is easy. 3 steps. Now suppose you had 3 disks to move from one pole to another. Call them little, medium, and big. Well, little goes to pole number 3, say. Medium goes to 2, so they're laid out big, medium, little on the posts. Now, little can climb on top of medium there. That leaves this pole empty, and big can move there. That looks good. Now, one can go to this pole temporarily, letting 2 climb on top of 3, and little can finally go on top of that. That wasn't so tough. If you counted, that was 7 steps for moving 3 disks. Perhaps you can see a strategy in the simple cases that we can scale up to 6 disks. When we went from 2 disks to 3, we really moved the top 2 like when we were doing just 2 disks, then transferred the big disk to the bottom, and then moved the top 2 again, like when we were doing just 2. I'll bet that doubling up of previous move patterns is going to happen with every additional disk. What if we try 4 disks? We'll go through the moves for the top 3, like we just figured, 7 steps, then move the super big disk on the bottom, Then repeat the shuffle of the top 3. That'll be 7 moves plus 1 plus 7, so 15 moves for 4 disks. You see the pattern? The problem with 2 disks took 3 moves. The 3-disk problem took that many moves, plus moving a bigger disk, plus that many moves again, 7 steps. The problem with 4 disks was really the 3-disk solution, plus moving super big, plus the 3-disk solution. So for 4 disks, it's 7 steps, plus 1, plus 7, giving us a total of 15 steps. Scale that up, and you can see the pattern for 6 disks. The minimum number of steps for 5 disks is the number of steps to move 4, plus a move for the 5th one, plus the number of steps to move the 4 on top of it again, 15 plus 1 plus 15, 31. 6 disks is going to be that, plus 1, plus that again, 31, plus 1, plus 31, 63 steps for 6 disks. Here are the strategies we used. Visualization. Then, going to extremes. In this case, that just meant going to the simplest versions, 2 and 3 disks. From those analogous problems, the basic pattern started to emerge. Divide and conquer was at work too. The 6-disk problem had the 5-disk as a component, the 5-disk had the 4-disk, and so forth on down. We started with an extremely simple form of the problem and bootstrapped up from there. There's some psychological evidence that that often works as a strategy. The psychologist John Sweller gave some college students a starting number, 8. That was their number in hand. They were told to convert 8 to 15 in exactly 6 moves. At each move, they had to multiply their number in hand by 2 or subtract 7. One group got just that complex problem. The other group got 3 problems. The first 2 problems were simpler versions, parts of the whole. For example, start with 8 as your number in hand. At each move, multiply your number in hand by 2 or subtract 7. Can you get from 8 to 9 in 2 moves? Not too tough. 2 times 8 is 16, minus 7 is 9. From 8 to 9 in 2 moves. But how about getting from 8 to 15 in 6 moves? The solution here is to alternate operations. You can get from 8 to 15 by multiplying 8 by 2 to get 16, subtracting 7 to get 9, times 2 to 18, minus 7 to 11, times 2 to 22, minus 7 to 15. So Sweller gave one group just the complex problem. He gave the other group 3 problems, 2 simpler ones like the move from 8 to 9 and the complex one. So who got the hard problem fastest? On average, those who got just the complex problem needed an average of over 5 minutes to solve it. Those who got that problem after 2 simpler ones needed only about 1.5 minutes to solve the complex one. This statistic is even more telling. The group presented with only the complex problem took over 5 minutes to solve it. The 3-problem group took an average of only a little over 3 minutes to solve all 3 problems. My colleague Marvin Levine, who gave me several of the examples in this lecture, says that someone faced with just the 6-disk problem of Hanoi will take maybe 10 minutes to solve it. He predicts that someone who spends 5 minutes thinking about the 2 and 3-disk case will need only another 2 minutes to solve 6 disks, for only 7 minutes or so in total. Not all thought experiments are out to prove something or to find the right answer. Sometimes thought experiments are explorations in a very different sense. There are imaginative explorations in epidemiology. If you didn't have vaccine for the whole population, where would it do the most good? There are imaginative explorations in economics. What changes in the financial structure would best stimulate employment? In business, many a startup triumph began in thought experiment. What if you could access digital information worldwide? What if you could social network online? Here's the thought experiment in the ethical realm, the runaway trolley. A trolley is running out of control down a track. The bad news is that it's hurtling toward 5 people tied to the track by a mad philosopher. The good news is that you're standing next to a rail switch. All you have to do is pull that lever and the trolley will go down a second track instead. The bad news is that the mad philosopher has also tied 1 person to the track on that side. What do? Do you do nothing, allowing the 5 people to die? Or do you pull the switch to save them, thereby sacrificing the 1? This thought experiment was originally presented by the philosopher Philippa Foot. It was designed merely to point up differences in ethical theory. As it turns out, it may also reveal differences in the way different people approach ethical problems. In ethics, utilitarians hold that the right thing to do is that which results in the greatest good for the greatest number. They would clearly pull the switch, sacrificing 1 in order to save 5. Would you? We can change the thought experiment at will. What if that 1 person on the second track is someone very special to you? Your mother, perhaps, or your child. Now would you pull the switch? Is that the ethical thing to do? A utilitarian would say it was. Here's another variation. This time there's no branch in the tracks. You're on a bridge above it as the runaway trolley rushes toward the 5 people. Only by stopping it with a large object can you save them. The good news is that there is a very large man sitting on the railing next to you. All you have to do is give him a shove. When he falls in front of the train, he'll be killed instantly, but his bulk will save the 5. Should you push him off? Would that be the ethical thing to do? A utilitarian would still say yes. But perhaps you're now less inclined to be a utilitarian. It's not just philosophers who are interested in ethical thinking. The runaway trolley has been used with fMRI scans to explore the parts of the brain that different people use when thinking about the problem. Joshua Green is a psychologist at Harvard who has done much of this work. The first conclusion he draws is that there is no single part of the brain devoted to moral decision alone. There is no ethics central. Moral judgment recruits various portions of your brain. Green claims that people who arrive at different decisions in the runaway trolley use a different balance of brain areas. If you refuse to pull the switch when someone important to you was on the track, and you refuse to push the very large man off the bridge, emotional centers of your brain played a major role. Those emotional centers play a smaller role for utilitarians, dominated by more cognitive centers, focusing purely on the numbers of lives lost. The implications of Green's work remain controversial. Can any brain scan tell us whether something is ethically right? That looks like a question we might explore with further thought experiments. We've looked at thought experiments in the history of physics, as well as the history of philosophy, and ethics and neuroethics. There's no rule book for imaginative thinking, but there are some general strategies. Visualize. Go to extremes. Simplify by analogy. Divide and conquer. In all these ways and more, give your imagination time to roam. The role of thought experiments in philosophy, physics, epidemiology, economics, and business make it clear that imagination isn't merely an escape from reality. Imagination is one of our finest tools for exploring reality. Imagination is one of our best routes in. In the next lecture, we'll return to simple visualizations that give us all the logic of Aristotle.